Welcome to this month ABC UTC monthly webinar. My name is Mary Lou Rawls-Newman. I'm Director of Technology Transfer at the ABC UTC and will be moderating today's webinar. Before we start our featured presentation, we'd like to make a few announcements concerning activities at the ABC UTC and from our industry partners. First, a few slides on our upcoming 2020 International ABC Conference, fully in person this year on December 7th through 9th in Miami, Florida. The deadline for early bird registration is August 26th. Please visit the conference page on the ABC UTC website for more information and to register. Also, as a reminder, that conference travel scholarship applications are due August the 22nd. A limited number of scholarships are available to state and local bridge professionals. The scholarships include 4 hotel night stays and registration for the pre-conference workshops and the conference. If interested, please go to the website shown on the screen to apply. As in the past, conference and workshop attendees will receive certificates of attendance. Also, for those of you in Florida and in New York, FIU is an official sponsor of continuing education. The online submission deadline for the conference call for award nominations is August the 22nd. This year, we have the same award categories as in the past, plus 2 new categories, a Best International ABC Project category and a Most Impactful Bridge Engineering Technology category. Please go to the website shown on the screen for more information and to submit your nominations. 4 half-day pre-conference workshops will be held on Wednesday, December the 7th this year. Steel bridge design and fiber-reinforced polymer composites bridge design workshops will be held in the morning, and pre-stressed concrete bridge design and non-proprietary ultra-high performance concrete workshops will be held in the afternoon. We very much thank our workshop coordinators and presenters. For more details, please go to the website shown on the screen. This month, the FRP Composites Bridge Design Workshop is featured in our news presentation. Topics for the FRP Composites Bridge Design Workshop will include design of FRP bridge tub girders, cantilever sidewalks for shared use paths on vehicular bridges, and infracore FRP vehicular bridges, in addition to an overview of FRP bridge case studies. Opportunities are also available for exhibitor booths. If interested, please go to the website shown on the screen. We hope you can be with us in December in Miami. Our presentation today features New Mexico's all-precast bridge, the NM50 bridge over Glorieta Creek in the Pecos National Historic Park. We'd like to thank Kathy Kroll, formerly with the New Mexico Department of Transportation, for coordinating this presentation. We're pleased to welcome our presenters, Shane Coleman, State Bridge Engineer and Bureau Chief with the New Mexico Department of Transportation, and Kimberly Coleman, Bridge Engineer Manager, also with the New Mexico DOT. We'd like to also introduce our Q&A session moderators, Paul Lyles, formerly Georgia State Bridge Engineer, and Jugesh Kapoor with WSP USA and formerly State Bridge Engineer at WashDOT. We'll now begin our featured presentation. Shane?
Hello, everyone. It's a pleasure today to have this opportunity to present on New Mexico's experience on the utilization of accelerated bridge construction. I would like to thank Mary Lou and ABC UTC for giving us the opportunity to present and highlight our work at NMDOT and in New Mexico. New Mexico is a large and diverse state with a challenging landscape. The detours for our bridge crossings can be quite long and create problems for users when bridges need to be replaced. The New Mexico 50 over Glorieta Creek Bridge was a recent accelerated bridge construction success that highlights our advancement in ABC in New Mexico. So today I'll give an overview of New Mexico's current ABC activities and initiatives. And then I'm going to pass it over to Kim Coleman, and she'll take a drill down approach, getting familiar with the project area first, and then all of the different cultural, historic, and space constraints at the site. Then we'll look at the existing bridge, including some investigations that we did to try and save it. In the end, it was determined that replacement was necessary. Kim will take you through the type selection process, which includes the ABC decision making. And then we'll take a look at some of the plans, design details, and finally the construction and lessons learned. In New Mexico, we've been working to advance the utilization of accelerated bridge construction. Currently, the I-25 Romeroville interchange replacement is in design. The interchange is the primary access to a truck stop to the west, and then frontage roads that access several residences in the area. And then to the east is the junction to US 84, which ties into Interstate 40. It's a lot of commercial truck traffic. It's heavily used. It's a very heavily used interchange. A long construction duration to replace the bridge would be very problematic and expensive. So the bridge type evaluation focused on ABC and was completed by our internal bridge staff. The project is now moving forward to phase 2 design. Also currently moving to construction in the state is a steel bridge, New Mexico 566 over the BNSF Railroad near Gallup, New Mexico. This is a very busy rail line for BNSF. It's the primary route from the ports in California to the east. There's not a lot of time between trains. So the design and construction approach is to erect the steel girders in pairs with all of the permanent bracing installed. This will provide stability during erection, minimizing the temporary erection bracing, and then also reduce the number of girder sets over the railroad by up to 50%. So although it's not a full ABC approach, it is utilizing many of the ABC techniques to reduce impact to the railroad and then users that need to cross the bridge, since it is one of the primary access points to Church Rock, the town right there. In New Mexico, over the years, we have been using prefabricated bridge elements for bridge construction, which is a primary and integral part for ABC. We've completed several projects recently that were originally designed to be constructed as an accelerated process. But when they got to construction, the contractor negotiated and basically changed the approach to be more of a traditional construction process. The two projects that I'd like to focus on are the Guadalupe Street Bridge deck replacement in Santa Fe, New Mexico, which is shown in the upper right photo. It was a precast deck panel, bridge deck replacement on steel girders. Everything went to plan until construction, and then it just extended and became more traditional. And then the other project was the rehabilitation of the Interstate 40 Indy interchange at the New Mexico-Texas state line. It also used precast deck panels and was our first UHPC joint connection project. And again, once it hit construction, it became more of a traditional approach. So based on those two projects, we felt that some internal education was needed for the other sections and our construction folks to make ABC more successful in New Mexico. We reached out to FHWA and applied for stick funding, and last fall we held an ABC workshop in Santa Fe. Mike Coleman with CHA Consultants came out and presented on how other states have successfully completed ABC for projects and focused on the process on the department side to make those successful projects. I feel that the training was very beneficial and will help NMDOT and us move forward with ABC for future projects. So the New Mexico 50 over Glorieta Creek bridge replacement, and that's the bridge shown in the right photo, was our most recent project that required ABC, and it was very successful. Later on in the presentation, Kim Coleman will give a detailed overview of the project, the success of the project, and lessons learned that will be key to NMDOT advancing ABC on future projects. With the recent federal infrastructure funding that has been given to the states and the ability to use it on local and off-system bridges, we're looking at ways to help the local governments in our state. We currently have a bridge replacement in design that has a good superstructure with good girders, but the substructure is poor. We're doing some preliminary design and feasibility analysis to repurpose the girders to help replace poor bridges, primarily in McKinley County, which is to the south of the project site and is located on and near the Navajo Reservation. It's anticipated in our preliminary analysis that an ABC approach will be the most cost-effective method for replacing those structures, since most of them are rural and there's no detour around them. New Mexico's goal is to advance ABC on our bridge replacement projects. The benefits to reduce construction time, impact to users, and worker safety are very important to us. Current inflation has had a huge impact on our overall construction costs and traffic control. and is a large portion of those costs. Last week, I was at the WashTow conference as a presenter, but I also sat in on a presentation by Graham Bettis with TxDOT, and he discussed how prefabricated bridge elements are primary components of ABC, and that bridge slides and moves with SMPTs aren't the only ABC methods. And I completely agree with that. And New Mexico has been using prefabricated elements for a long time. What we need to do is focus more on the construction process, sequencing, and then the contract language to advance ABC. Graham also discussed how they have modified their design procedures for bridges to advance ABC. In New Mexico, we currently use the Wisconsin DOT flowchart to screen ABC for our projects, but somehow in the end, it usually gets flushed out and ABC isn't the primary method for construction. I would like to modify our design procedures to be similar to what maybe TxDOT has done to advance and make ABC more viable in the screening process, because I think the benefits are good for everyone involved. Just to highlight on this slide, the bridge in the photo is the I-25 Las Vegas Airport interchange bridge replacement that was done several years ago. It was a 45-day bridge replacement project, and the highlights of that project were it was an ABC project. Full height abutments were built under the existing structure. The pier was constructed under the existing bridge on a spread footing, and then it was also featured in Aspire magazine as a very successful ABC project for our state. Recently passed legislation in New Mexico, I believe, will help advance ABC going forward. Our legislature recently passed CMGC, and we had a cap on design build projects, a minimum cap. I think these alternative delivery methods will help advance future use of ABC in our state on projects. Our most recent design build project was the Paseo del Norte interchange shown in the photo. It is an example of a project in New Mexico that would have benefited from more ABC techniques to complete the construction faster and reduce the user impacts and detours and delays with construction. Going forward, our priorities will be to maximize the utilization of the federal formula bridge funding to address our off-system state-owned bridges that haven't had the attention they've needed over the years due to lack of funding, and also to help the local and tribal governments rehabilitate and replace their poor bridges. They have also been impacted and limited on what they could do by funding and engineering capabilities. So we want to help address their bridge since it's a significant need for our state. And then finally, as discussed previously, our goal is to advance ABC for future bridge replacements and hopefully resulting in more successful projects like the New Mexico 50 project. So before we get into the meat of the New Mexico 50 project, I'd like to familiarize everyone geographically. New Mexico is in the southwest part of the country between Texas and Arizona. Albuquerque is our major metropolitan and is centrally located in the state. Santa Fe is the location of our general office for NMDOT and is located approximately 60 miles northeast and is at the base of the Sangre de Cristo Mountains. As you can see in the blown up video, maybe a little hard, but you can see where Albuquerque and Santa Fe are located there. So here's a blown up view of the area showing Santa Fe and the location of the New Mexico 50 project. The bridge site is located just outside of Glorieta, New Mexico, to the southeast of Santa Fe. And just to note, as many of you may have seen in the news recently, our state has been experiencing unprecedented wildfires due to drought conditions. Shown is an approximate outline of the current burn scar, and you can see that the project location is very close. President Biden actually just visited New Mexico and toured the area and flew it to assess the damage and has agreed to help fund the wildfire relief efforts here in New Mexico. Now that I have given a brief overview of ABC in New Mexico, I'm going to pass it off to Kim Coleman, the bridge engineer manager and designer of the New Mexico 50 bridge project, and she will provide a detailed overview.
Thanks, Shane, for that excellent introduction to the project area. Now let's drill down a little bit into the details. So the New Mexico 50 Glorieta Creek project was a traditional design bid build project at a total cost of $2.1 million. The contractor was limited to a 7-week road closure, and they made it. The bridge was open to traffic 1 day early. and the project was completed with no claims. So this was a very successful project for us. NMDOT is the owner of the road and bridge, but I believe our right-of-way is actually an easement through National Park Service land. The project was designed entirely in-house here at NMDOT with bridge, roadway, right-of-way drainage, geotech, traffic, environmental, and cultural resources all happening in-house. AUI was the sole bidder on this bridge, and they were awarded the project. All the pieces were cast at Castillo Precast, about 25 miles south of Albuquerque in Belen, New Mexico. And UHPC was from Lafarge, and it was their ductile product. Our spec did require for this project that the Lafarge representative be on site during the UHPC pours because we wanted to make sure we had their advice as things were going along. The project had a lot of stakeholders. As I mentioned, the National Park Service owns the land around the project. We also had the New Mexico Department of Game and Fish involved, Santa Fe County, the Santa Fe Regional Emergency Communications Center, including nearby fire departments, and also the Santa Fe Public Schools Transportation Department. NMDOT's relationship with all of these stakeholders remains good, even at the end of the project. So that was an achievement, I think, for our planning and execution folks. Disincentives were part of the project. As we walk through some of the environmental and historic constraints of the site, some of these will make a bit more sense, but the main ones to pay attention to here are the $10,000 a day disincentive for exceeding the 7 weeks of full road closure on New Mexico 50, and also the limitations on work areas and staging areas. You can see on the left here, we were limiting how they got down into the stream, and we told them they could only demolish and place a crane and stage in limited areas. Everything from the Western Bridge approach, and no parking on Park Service lands. So we had to really limit where we walked and drove to preserve the site. Here's a map of kind of a zoomed in map of the area. As you can see here, Santa Fe is just to the south. This is actually northbound, the direction I'm going here, even though the interstate takes a jog. The project site is just over 1 mile east of the I-25 Glorieta interchange on New Mexico 50 at milepost 1.15. Note here we have Pecos to the right on New Mexico 50 and Row down I-25. This project area, as you can see from the purple in the middle of the map, is owned by the National Park Service and is within the Pecos National Historical Park Pigeons Ranch unit within the Glorieta Pass Battlefield National Historic Landmark. And this was the main battlefield of the Battle of Glorieta Pass during the Civil War. So you can imagine we had some constraints in this construction. Here's a zoomed in map. The detour route for this bridge was 18 miles long. And so as I mentioned before, we have Pecos here and Row here. So if you live just east of the bridge and you want to go to Santa Fe, you have to travel east on Highway 50 to Pecos, south on Highway 63, and then back southbound on I-25 just to get 1 mile towards the interstate. Quite a few people live on New Mexico 50 just east of the bridge and commute to Santa Fe regularly for work and shopping. School buses use the route for getting kids to school. So we knew if we had to close it to replace the bridge, we would have to get it back open quickly. And we did consider phasing, by the way, and I'll talk some more about that as we go, but it wasn't really a viable option in the narrow right-of-way. So with the bridge out for 7 weeks, we had two main concerns: school buses and emergency responders. We anticipated that the summer closure might extend into the school year. So we were in communication with the school transit department so they could plan their bus routes accordingly. And we were also concerned that emergency response times would be too long due to the 18-mile detour. So with cooperation and coordination with the National Park Service, we were able to establish an emergency detour route, which is shown here. This is the bridge right here. And as you can see, the emergency route comes off New Mexico 50 on a local road and connects to the old Denver Highway, which actually has an old on-ramp to the interstate. In the end, it was never used, but it's a great example of pre-construction coordination and included a formal legal agreement between the NMDOT, the National Park Service, Santa Fe County, and the Santa Fe Regional Emergency Communications Center. Now we'll get a little bit closer in. The project area, as you can see here, extends 400 feet east and west of Old Bridge 397 within the NMDOT easement, which here's the easement. It's only 60 feet wide. And you can see Old Bridge 397 here in the middle. In our coordination with the National Park Service, we learned that minimizing ground disturbance was going to be very important in this area. So Bridge 397 itself is not eligible for listing as a historic property on the National Register of Historic Places, but we do have other historic structures in close proximity. So the images on the slide show here the historic Pigeons Ranch building and then a stone well, both from the Civil War era. You can see the stone well also in this picture, and here's the Pigeons Ranch building. Here you can see some trees adjacent to the stone well, and you think to yourself, well, trees, there's plenty of those. But these were identified as witness trees, meaning that they were old enough that they were probably already growing there during the Civil War. So they were identified as needing to be protected during construction. Downstream of the bridge here, just off the bottom of the slide, is also a wetland. And because this was part of the Glorieta Pass battlefield in the Civil War, there could be artifact scatter from that time period. And so to mitigate all of these concerns, we had a monitoring plan for construction, which included vibration and crack monitoring on the Pigeons Ranch building and observation of any site disturbances, especially drilled shaft construction in case we would dig up anything of historical significance during that drilled shaft construction. Since this was an ABC project, our Environmental Bureau coordinated a preliminary survey of the area prior to starting of construction, and that way, hopefully we could find and mitigate any historic sites before we got started with the road closure. Here's a couple more pictures of the existing site. This is Glorieta Creek looking upstream underneath the bridge, and then here's a picture of the existing bridge from above. You can barely see that it's a bridge, especially since we used W rail back in the original construction as the bridge rail. So here's another picture of the existing bridge. Note the non-standard railing here, posts and a W rail, and also note the heavy deterioration of the deck edge. Because of the condition of this deck edge and the railing connections to the deck, one of the first steps we took during project planning was to get the crash records, especially any kind of crashes caused by lane departure, because we wanted to make sure as we were planning that we weren't going to have accidents before we had a chance to replace it. And then also here, note the wealth of greenery, which is pretty unusual for New Mexico. So that may be one of the reasons the Park Service wants us to be real careful with it. Again, a profile of the original bridge in the upper right. This was a 22-foot span cast in place, mild reinforced concrete T-beam bridge built in 1923. And in all of our bridge records, we could only locate one sheet of plans for this bridge. Here at the bottom of the slide, you can see a typical section taken from the standard drawing, which was the only sheet we had, showing the original superstructure typical section. The rest of the standard shows beam sizes and rebar tables for a 23-foot wide superstructure of 6 different possible span lengths. We didn't have any other drawings, including substructure, nothing. So you're hearing me say that this is a concrete T-beam bridge, and you're looking up here and seeing a steel girder and saying to me, what on earth is going on? Well, somewhere between 1977 and 1979, the superstructure was widened from 23 feet to 33.5 feet. First, they widened the substructure with reinforced concrete abutment walls and wing walls, and the superstructure was widened with one steel girder on each edge, but we do not have any drawings for this. And we believe that the work was done by our in-house maintenance forces. So because of the existing superstructure width and the load capacity, I'm going to talk now about why phased construction was probably not the way we could go. We did consider repairing the bridge. And the reason that was attractive to us is first the 18-mile detour, the fact that we had a lot of environmental and historic considerations on site, and also we only had 60 feet in width. We did, however, consider that we had to replace it for the below reasons. 33.5 feet is the total width of the bridge, and the rail is in terrible condition. So we didn't want to be pushing trucks closer to the rail. The load rating was not very good, we had it at 11.3 inventory and 18.8 operating. And we also chose to do non-destructive testing because we wanted to know for sure what kind of bridge we had out here. We ended up doing GPR, sonic, ultrasonic impact echo, velocity testing, half cell testing, chloride measurements, and carbonation measurements. So we wanted to know everything since we didn't have any plans to speak of. What we found is we actually had a couple of locations on the beams that were 600 PSI. This is supposed to be 2000 PSI concrete, but it wasn't. And then we do have locations in those beams with active corrosion. So in the end, we determined that replacement really was the only option. Make our ABC assessment, we used the ABC decision making matrix from Wisconsin DOT. This gave us a score of 28, which indicates prefabricated bridge elements and systems. As we've already discussed, the detour is long and it affects the emergency vehicles and school buses, and our right-of-way is very tight, so we couldn't safely phase construction. We also have significant environmental and cultural restrictions, and there is very limited space for construction staging near the bridge. We did have to use the roadway during closure for staging and materials, not much shoulder off this bridge. So having an accelerated schedule helped to minimize the amount of time, material, and machinery had to be stored on site. And finally, the National Park Service had many concerns about construction disruptions to the wildlife, the foliage, and the historic look and feel of the site. Here at the bottom of the slide, you can see a before and after photo. And it's hard to see here, but the bridge is right here in the before and right here in the after. I think we did succeed at preserving the historic look and feel of the site. And I do also want to mention the Natina coating. We used a brown coating on the galvanized bridge rail to make it look brown and blend into the W rail, the weathering steel W rail that Roadway chose to use. Okay, now for bridge type selection, we compared a precast concrete slab bridge and a prefabricated modular steel bridge. From the National Park Service and the Environmental Bureau, we had to consider several things. First, they wanted us to minimize disturbance in the creek and the surrounding area. So our design and specs worked to minimize excavation, scaffolding, equipment, and demolition and construction debris. And we even kept construction foot traffic within our 60-foot easement. We also needed to minimize vibration, so that drove us to use drilled shafts rather than piles. The structure needed to have an open bottom, and this came from the New Mexico Department of Game and Fish. They asked that we maintain the ability for all animals, fish, and invertebrates to travel up or downstream uninhibited. So a culvert was out. We couldn't have a closed bottom. And then they also asked that the railing have a rustic, old appearance, and that is why we chose to use that brown Natina coating. So the new bridge is a 35-foot wide, 40-foot long single span precast concrete slab with open metal railing. The existing concrete abutments were preserved to minimize ground disturbance within the channel and the historic landmark, and to maintain existing flow characteristics of Glorieta Creek. And all of these things work together to minimize disturbance to the critters and the wetland, and also any historic artifacts that might be located on site. So our ABC project elements here, we had a road closure duration limited to 7 weeks. Originally, we were trying to replace the bridge in 2 weeks because the district personnel were so concerned about the emergency vehicle access. But as discussed in our earlier slide, we were able to mitigate this with the temporary emergency detour. So we didn't need to go quite that fast, but we still wanted to minimize the construction duration for the residents just east of the bridges. A few other things, we originally had 3 shafts per abutment, but to save time, we worked with Geotech to find a configuration where 2 shafts would work. We also used entirely precast caps, wing walls, girders, and approach slabs. All the elements for the bridge were precast except for the drill shafts. We chose metal rail, and we detailed those rail anchors to be cast into the precast beam, ready for the rail to be bolted on. Precast concrete rail would have been heavier for the crane to lift, or we would have had to form and cast that concrete on site. And our NMDOT spec does not allow for slip forming, so it was going to have to be the traditional form and cast concrete rail. So we chose metal instead. We also had the contractor do a UHPC mock-up pour in the precast yard just to get them familiar with how the UHPC pours and works and sets and leaks out if you don't have a watertight seal. So that was a time saver during construction. We use just-in-time delivery. As I mentioned, the I-25 Glorieta interchange is about 1.2 miles away from this site. There's no room for a truck to turn around once it gets to that site. So our delivery just ended up having to, the trucks had to pull off at the I-25 interchange and get oriented to back a mile down the road to the bridge site to deliver these pieces, which was some excellent driving. And again, at the end, we chose Uhpc Connections for speed of cure so that the contractor could proceed with their critical path tasks sooner. Not much forming involved because the precast pieces ended up being a large part of the Uhpc formwork. And also there's less material to mix and haul because the joints could be narrower. And also we could avoid waiting for concrete trucks. Here's a plan view of the bridge. As you can see, we have the 40-foot span and a 35-foot width. One thing I want to point out here, as you can see in the contours, these are the existing abutments, and those are what we were going to preserve. Here's a nice photo of the site with the existing bridge still intact. The abutment backfill has been excavated, but this is before they did any demolition. On the profile view, you can see the existing substructure and the new shafts behind with the permanent casing. The existing abutments were to be saw cut just above the 100-year water surface elevation to keep everything dry during floods, but to allow enough headroom here for inspectors to get in there and for future bearing replacement. For the shafts, in the drawing on the upper left, you can see the drilled shaft here with a 42-inch casing, permanent steel casing. The top of this casing here is the level surface on which the precast cap was set. Also note the leave out in the abutment cap. This is formed with corrugated metal pipe, and you can see how the rebar cage projects from the shaft into the cap. The plans required that the shaft concrete stop 1 inch below the top of the permanent casing so that UHPC could be poured down the top here into this area, and that would make a strong connection between the shaft and the cap. Here to the right, you can see a photo of the drilled shafts going in, and down at the bottom, during shaft construction, we have a photo of the vibration monitoring that was done for the Pigeons Ranch building. Here on the left is a picture of the permanent casing being lifted into place for the shafts, and then here on the right, you can see the completed shafts with this cross-hole sonic logging tubes ready to do our shaft testing. Note that the rebar could be this short due to the UHPC we used in the connection. And here is that permanent casing level to set those caps on. In our design, this is the existing abutment. We did investigations to understand what we had since we didn't have any plans. We did some non-destructive testing and bore holes to understand how thick the concrete was in the original abutments. And we also did some low strain integrity testing to try to understand the depth of the abutment wall. And it turns out that this abutment wall is embedded 3 feet into bedrock. Because of that, and because it was not so thick that it conflicted with our new substructure, we determined that it was beneficial to leave it there. It would protect the new substructure from scour, and it would preserve the existing look and feel of the site. Also, it would preserve the flow characteristics of the creek. However, it was a bit too tall, so we have this drawing here that shows how they could saw cut the top of the abutment off. We did have this reinforced concrete area on either side from the widening. And we learned that it was reinforced during the non-destructive testing. So what we did was we pulled that down a little bit further, and we spliced some new pieces of rebar on and also put in some anodes to extend the life of that reinforcing. The contractor came up with a really great way to quickly remove the top of the unreinforced abutment and get a clean, smooth, and finished surface. So you can see a kind of a guide rail here that they mounted a circular saw and just sawed the top off. There was some chipping around the existing rebar up here, but otherwise it was a really great surface that they finished with. Unfortunately, I did not get any more pictures of the demolition, but I do want to mention the contractor ended up pulling this bridge out by saw cutting the superstructure apart and attaching lifting devices to each piece and lifting it away from the channel onto a truck and hauled off. So there was very little debris and no need to get heavy equipment down into the creek for cleanup. Now let's start putting the new bridge together. On the upper left, you have a photo of the cap here being backed down New Mexico 50 to get to the bridge site. And from this view, you can see the roughened surface keyway and bars for the wing wall connection. And I also want to point out this little ledge up here. This is where the approach slabs will sit. In the upper right, you can see a photo of the cap being lifted into place in the tight right-of-way. This is the kind of south side of the road, and this is the north side of the road. And the contractor was not allowed to trim or damage those trees. So they had to pick this cap up off the truck and keep it aligned to the roadway center line as they swung the crane to get the cap towards its final location. Here in the lower middle, you can see the cap almost ready to set down in place. And this is the guy who was making sure that it got set down right on top of the shaft bars properly. Note that the shaft casing, remember, needed this seal right at the top here, because this is going to be the watertight seal that holds the UHPC in the connection. This turned out to be a problematic detail, and I'm going to talk about this in the section on lessons learned, because it has also to do with how we handled the drilled shafts. But for now, I do want to ask you to keep this detail in mind, and note that there's not much room for error in getting those caps set down in the right place. Here in the lower right, we have just a view looking straight down into this cap annulus here, and just above the photo here, we've got a kind of a picture. You're looking straight down here, and you can see the shaft bars, and you can also see how tight it fits into that annulus. And we'll talk about that, as I said, in lessons learned. Here's our wing wall. The upper left shows a clip from the design plans. And again, here's that ledge that the approach slab sits on. In the upper right, we've got a photo of one of the wing walls being lifted into place. And then here on the lower left, it's set and ready to be connected with the UHPC right in here. Here's the detail of that joint from above, and then looking down in, you can see it's formed up and ready to receive the UHPC. Here are our precast slabs. On the left, again, a clip from the design plans. Up here, you can see where we placed the anchorage for our bridge rail, and then also the shoe plate on the ends of each girder. Here on the low side, you can see a typical interior girder, but I do want to point out the center slab actually had the crown cast in. So we were trying to limit the amount of time they were going to have to grind the normal crown into the bridge. So the precast slabs were set on the crown. The center one had the center of the crown formed into it. So all they had to do was just grind the UHPC joints smooth as a time-saving measure. Here on the upper right, you can see our joint detail for between the UHPC slabs, and this photo is of one of the first slabs being set onto the new abutments. Our approach slabs ended up being pretty complicated. We wanted a buried approach slab for paving and a smooth transition, but we also had a lot of other stuff going on. We had the Uhpc connections, we had the normal crown on the roadway, and we needed this level area for the metal rail posts to connect. We also had to limit the size of the pieces so the crane could lift and set it from across the creek. And this ended up being complicated enough. Oh, I do want to point out here, we also have this turn down to minimize escaping fill from behind the wing walls. So these ended up being complicated enough that my team had some difficulty making sure that we had clear and enough detailing. Because of that, the precaster had some difficulty getting these constructed correctly. So you want to be careful with the pieces and make sure you don't make them so complicated they can't be built. Okay, here's on the upper left a photo of all the pieces in place, and we're getting ready for the UHPC pour here in these other two photos. And shout out to one of our EITs in the NMDOT Bridge Bureau, right there in the middle. I don't know if he knows I caught him in that photo. Okay, we did have a diaphragm here. So in the upper left, we got a clip from the design plans showing the small diaphragm at the girder ends. This was to provide protection to the slab ends and to the strands that project from the slab ends. We also wanted it to tie the structure together for lateral loading and provide a smooth surface for our silicone joint seal that was going to be right here. In the right photo, you can see these bent strands coming up from the girder ends, and also here's the thread rod faithfully wrapped in pipe insulation and duct tape. You'll notice in this photo that the contractor worked really hard to seal up all those joints and make sure we didn't get any UHPC in the bearing area where it didn't belong. In the middle photo, I do want to point this out right here. We had to provide a bulkhead in this diaphragm at the recommendation of Lafarge to minimize the distance that the UHPC would flow, because this UHPC in the joint and this diaphragm can all flow into each other. So we wanted to minimize that distance. Here they are pouring UHPC. So on the left, they started by suspending the mixer from the crane and just pouring directly into the joints. And then I think as they went along, they thought maybe a bucket might be a better idea. And then here they were starting to get a system towards the right where they were using those 5-gallon buckets for all of the joints. Here's a photo of the finished bridge with all the vegetation looking really great. So they succeeded at keeping that in good shape. You can also see this dark brown coating on the bridge rail. That is the Natina coating on the galvanized rail to make it look rustic and old. So let's talk about some lessons learned for our future ABC projects. I think we should provide a suggested submittal timeline. This is typically a means and methods thing, but in New Mexico, our contractors have not been asked to do a lot of ABC, so I think a little bit of guidance on that might be welcome to them. On this project, even though we requested that submittal early, it came with very little time to spare before the precast production should have started. And of course, it required revisions. So we had to make sure we got all of that figured out before we started the 7-week closure. I think in future also, we should identify a backup submittal reviewer ahead of time, someone who's familiar enough with the design plans and the schedule to the extent that they could provide a review. It happened during our project that our 3-person design team received the 47-page precast submittal after one of us had been reassigned to another group and one of us had a death in the family. So all of our team's work was being handled by a single person. And that gets pretty hectic, and you've got to make sure you get these submittals turned around. So a backup reviewer would have been a good idea ahead of time. Also, we had pandemic delays. Nobody, I think, could have anticipated how heavily that would affect a project. But we did have key construction activities occurring when some of our staff had to isolate. So we ended up having to get some consultant help to fill in and be on site and monitoring things so that our other employees could isolate due to COVID. So now on to the elements for the drilled shafts. The drilled shaft cages were within spec tolerance. The NMDOT spec allows up to 3 inches out of plumb for our drilled shaft cages, but on this project, we had to get it to fit in the annulus on the caps, and we needed those caps in the right place. So with that NMDOT spec tolerance in mind and the shaft to cap detail that we talked about earlier, and the need for that casing and cap to be well aligned to get the watertight seal for holding the UHPC, it would have been a good idea to tighten that tolerance for this project. Another thing on the drilled shafts, don't let your shaft contractor be in a rush. This is our only cast in place element, and if we don't get this right, we're not going to have a good bridge. It happened on this project that we had a good rainstorm after the drilling and before the pour, and the shaft subcontractor did not take the time to clean out the bottom of the rock socket prior to the pour. So we ended up with low strength concrete in the bottom 3 feet of our socket, and we had only 2 shafts per abutment. So we really needed those to be right. In the end, we had enough extra capacity that it was fine. We could accept it, but if that hadn't been the case, we would have had a real mess. For the precast, it's a great idea to get the shop drawings in early, as we mentioned, and a fully precast bridge has a lot of shops and a lot of review time is required, especially for those approach slab pieces. So get those in early, especially for shop drawings where we need to have resubmittals. We did hire a consultant inspector to go to the precast yard and verify things like rebar location, spacing, compliance with the spec. So it's good to have eyes in the precast yard. NMDOT has recently been strengthening our precast specification, and we're also having to reestablish our inspection program after quite a bit of staff turnover. So our precasters during this project were getting used to having inspectors on site more often. And what we found is that they had become kind of comfortable making changes on their own instead of going back through the shop drawing process. So that was something that we had to kind of adjust as we were going on this project. And that is why we have this last item here, having a robust system for handling field changes. Okay, our Uhpc connections. We need to be careful of hydrostatic pressure. Again, from our discussion of the abutment cap, we needed to have a watertight seal between the top of the drill shaft casing and the bottom of the cap. The contractor chose to use a product called ram neck around the top of that shaft casing to make their seal for the Uhpc. Unfortunately, when they were setting abutment 1 cap down, it didn't go down in quite the right place to begin with. So they ended up lifting it to adjust, and the ram neck partially stuck to the cap and partially to the casing. The right thing to do, I think, would have been to stop and put that ram neck back and try to set it back down again, but they went ahead and just set it and left it. So on one of the abutment 1 shafts, we did not get a good seal. And as you can see in this photo, we ended up losing quite a bit of Uhpc. Here's the annulus, and this is what we were filling, and it just squeezed out from underneath the cap. So that was pretty expensive right there. Because of the height also of the cap to wing wall connection here, we also lost a little bit of Uhpc from the wing wall joint. It's kind of squeezing out like toothpaste. This one was easily fixed. We just pressed that form a little tighter using a 2x4 kicker, and it stopped. But this one was tough to stop. For top forming, we did not require top forming in the spec, and the contractor elected not to top form. So in the higher spots of the deck, you can see here the Uhpc settled and didn't completely fill. I think we have fixed that in our spec now, but it's something to keep in mind for our future projects. And then on the bottom here, as I mentioned, the Lafarge representative recommended that we install these bulkheads. So understanding the flow limits and how the pores are connected together is important for getting your bulkheads installed in the right place. Okay, so that completes my presentation, and we'll be happy to turn it back over and take questions.
Thank you, Shane and Kimberly, for your excellent presentation. Very interesting project. Paul and Jagesh will now moderate the Q&A session. Paul?
Thank you, Mary Lou. And yeah, Kimberly and Shane, really an interesting project. We've got a few questions that came in during your presentation, and there'll probably be more that come in during the question and answers. So, and there were some questions that came in before the presentation also. The first thing I'm going to ask is there's a couple of questions that came in, and I'm going to ask Shane possibly to answer these. These were on your initial presentation about the background in ABC. The first one was, how was it that ABC design projects were able to be revised post-letting to conventional construction, and was it through a value engineering process?
Yeah, basically that was the approach it took, was value engineering, and they kind of negotiated after the fact with the districts, because New Mexico is broken into 6 districts and each one kind of operates a little differently. But based on some of the risks that they considered, they negotiated and value engineered out going full ABC on those projects. Okay. They still maintain some of those, but they value engineered out a lot of it.
Okay. The next one was you mentioned having a workshop, and they said, how did you get buy-in participation from non-bridge personnel for the workshop? And then also, how long did the workshop last? And then have you noticed a change of ABC attitude on the construction side?
To get buy-in, I have a pretty good relationship with my manager and upper management, and I've been pretty proactive in just trying to educate them on the benefits of using ABC and how it can benefit the state, mainly with the other aspects outside of bridge, like safety, reduction in detours and traffic control, which is becoming a big issue, especially on our interstates. And then what was
Okay.
the other part of the question? Sorry.
Let's see. Have you noticed a change in ABC attitudes since on the construction side of your department?
I think that's the thing that we need to get more outreach and push more going forward is the construction side and maybe having a workshop or education with our contractors. So that's my next step in trying to advance ABC here.
Okay. Now let's move on over to the project, and we'll look at some design questions that came in. The first one, this is came in beforehand. And it says, what were the main factors to determine the use of ultra-high performance concrete instead of traditional concrete precast structural elements, segments?
Yeah, the connection size, so the length of the rebar that we had to keep in the connection was one of the main ones, but also we wanted them to be able to proceed since they were going to have to use UHPC to connect elements that they were then going to have to build on top of. We needed that curing speed and the high strength quickly.
Okay. This question came in beforehand, and you pretty well answered it in your presentation, but then there's some other questions that were new that were around this. And the question that came in beforehand was, were the abutments on piles? They were on shafts. You showed that pretty well. But we had a few questions related to the shafts, and this came in during the presentation. And the first one was, what was the length of the shafts? And how long were they, and maybe what were they founded on? Was it rock or was it soil?
Yeah, they were rock socketed in, and I believe we had a 10-foot rock socket, and so the shafts would have been about 20 feet long. They were very short.
Okay. What'd you do with the spoil?
I think they had to truck it away. They couldn't drop it anywhere.
Okay. And then there was another question here about this. It says, in the design phase of it, was a straddle bent considered, maybe drill shafts outside the existing roadway limits? You may not have had room for that.
Did actually think about that, but as we were trying to keep the span as short as we could and minimize the construction time and keep the existing abutments in place, we ended up just going inside the existing kind of abutment U shape.
Okay. Now that's real good. We'll move over to the construction side of it. We've got more questions along that line. Here was one. Can you provide an explanation of how you perform vibration monitoring of the old building? You might go look at that slide. You showed it being put in.
Now, I myself wasn't part of the vibration monitoring,
Okay.
so I don't know exactly how they did that.
The cases that I've seen where it was done, they put in a little seismograph and they can physically monitor if there's shaking. If it gets above a certain threshold, they say, well, we got to stop and think up something else. Yeah. There's the picture there on the left. I couldn't tell. What are those piles? Are those piles there next to it?
Those are actually the
those are guardrail
posts for the the guardrail posts. Yeah.
Okay. All right.
And because of the proximity to the building, they actually had to hand dig those posts in. Okay.
All right. These are neat questions that people are coming up with. Let's go on here. Another one that came in beforehand was, how successful was the contractor in achieving the design strength for the ultra high performance concrete in the joints between the precast units?
We had absolutely no issues with concrete strength.
Okay. Then were there any issues encountered during construction that altered the schedule? And if so, how were they handled?
Yes, we had our precaster unfortunately abruptly lost a large number of employees after fabrication began. So they had a little bit of a hard time meeting their schedule. We had a lot of rain in the area, which was saturating the backfill. So AUI had to do some aggressive work to dry out that soil before they could put the backfill in. No, Shane and Kathy, you're welcome to chime in, but I think those were pretty much the main issues.
Yeah, I think the only other one to add was that there was that alignment and geometry issue that we had the RFI on that wasn't reflected in the as-built or our initial design, and they had to chip out the corner of that wall to get that cap to sit in.
Okay. There's another question that came in beforehand. What issues, if any, did you run into with the precasting of several components of the bridge and having to move them on site?
Yeah, you know, we didn't have any troubles with moving them, I don't think. That was a very smooth process, but we did have some pieces with flaws, and most of them occurred on the approach slabs, the really complicated pieces. One of the header curbs had a strange sag in it, and let me try to find that slide for you. You can kind of see what we had to do. Here it is. It had this weird sag in it. We ended up having to chip out some of that concrete and fill it up with UHPC. And then also some of the bolt projections on that approach slab for the metal rail anchorage were insufficient for the double nuts that we usually install. And we had to come back in at the end and actually weld those nuts to those few bolts that weren't long enough.
Okay.
And just to add to that, Kim's group did a really good job up front looking at all the challenges associated with getting the precast elements delivered. She worked with bridge management section to make sure she wasn't exceeding weights, and that was one of the things that, if I recall, that pushed out using a straddle bent was just the size and length of the straddle bent to access and get delivered on site.
Okay. How far did they have to haul the members from the precast yard?
So that's about, let me see, the precast yard is 25 miles south of Albuquerque. So I would say about 120 miles.
Okay. And just in time delivery. That's pretty.
Just in time.
Good. Okay. Another question that came in beforehand, what was the biggest engineering challenge the contractor had to overcome that wasn't designed by the engineer of record?
I think that really the only design work they needed to do was on the demolition plan and how to get that old bridge out of there safely. They did also have some learning to work with the UHPC.
Okay. There was a question that came in beforehand about what were the lessons learned for this project. Kimberly, you covered that pretty well. I don't know if you want to add anything to that at all.
I think unless Shane and Kathy have something to add, I thought pretty hard about how to include it all in the presentation. So.
Okay.
Yeah, I think you did a good job covering them. I guess if you can anticipate a global pandemic and labor shortages, that would be the only things to add to the list.
Well, one thing I would add is, again, you know, it's sort of the Kim show. She and her team just did a fantastic job. But as everybody knows, with the ABC projects, you have to be really responsive to RFIs and just really be available. So I think that's a lesson that we all have to learn, is to make sure that we have the management staff available, even on nights and weekends, if it takes that, to make sure that we can respond and work with the contractor to overcome any potential issues.
And to add to that, I think the proximity of the site helped with being able to get to the site in a timely manner to help answer field questions as well.
Okay. We'll move over to a cost question, and then I'm going to turn it on over to Jugash. There are a few more questions that are still coming in. The question on cost was, what was the cost of the UHPC, and were there any issues with the contractor being able to supply it?
So the UHPC was $18,500 a cubic yard. So that was a total cost of almost $124,000 for the bridge. There was a time before we actually got rolling in construction that we thought we were going to have trouble getting the steel fibers, but thankfully Lafarge assured us that they had enough of a stockpile on hand that we could complete this project.
Okay. It's a few minutes after the hour, so I'm going to go ahead and turn it over to Jugash. We have a few more questions that came in during the question and answers, and he'll go ahead and ask these. Jugash?
Thank you, Paul. So first question, this came in during the presentation, and it's asking for the length of the cast-in-place drill shaft.
We answered that one.
I think we answered that. It was about 20 feet.
20 feet? Okay, thank you. The next question is, was a straddle bend considered outside the existing roadway limit?
Yeah, I think that one we might have answered as well. It was originally, but as Shane also mentioned, we had to pay attention to the crane lifts and the weight of each of the pieces. So the smaller we could go, the less smaller size crane they could put in there. And that was important because we had to pay attention to the crane swing within the narrow right-of-way.
Okay, can you comment on the UHPC strength data? What was the strength of the concrete?
Final strength is 21,000 psi, and we were getting 14,000 pretty quickly. It was, I think, within a week.
Okay. And leading on from that question is another one on UHPC. It says, it's asking why, I don't understand why UHPC has been used in this particular project, actually. What was the real need for it?
I think we had touched on this a little bit earlier, but if you think about it, you have the shaft to caps connection. That's got to solidify also the wing wall to cap connection before you can start setting the precast slabs on top. And then the approach slab and precast slabs all have to be hardened up before you can pave and open the bridge. And so it really was, the main driver was speed.
Okay, thank you. Next question is, why was the UHPC joint kept so narrow? It obviously was a challenge for the pouring of the UHPC.
Cost. We were trying to minimize the amount of UHPC we had to use, but we did provide some, I think I can show this. As you can see here, let me get the pointer up. You can see we did provide these pour pockets. So every 10 feet, we had a pour pocket to help them have enough room to pour that in.
Okay, thank you. Next question, with the use of UHPC, what was the rebar consideration? 60 KSI, 80 or 100? Corrosion resistance a consideration also?
Yes, in our slabs, because this is an aggressive environment, because we have salts and de-icing chemicals on this route, and also because the precast slabs are the driving surface, we used 100 KSI Chromex in the main superstructure. In the rest of the bridge, we used 60 KSI black bar.
We also added some sacrificial thickenings to the top of the slabs to provide for grinding, but also just to add additional protection to the reinforcing steel over time.
Okay, thank you. Next question, I'm interested in early strength of the UHPC within hours or days, since this is ABC. I don't know what the relevance of that is to this project, but do you have any information?
Off the top of my head, I don't. I would have to go and ask our construction folks what the cylinder breaks were for the very early stages, like 2 days, 4 days.
Okay. I think that pretty much wraps up all the questions I have on my list that came in during the webinar. So thank you very much for the answers. I'll turn it back to Mary Lou.
Okay, thanks again, Shane and Kimberly, for sharing New Mexico's ABC activities and your challenging NM50 bridge replacement project. Thanks also to you both and Kathy for your thoughtful responses during the Q&A session, and to Paul and Jagesh for moderating the Q&A session. Thanks also to Ali Javid, PhD student at FIU, for managing the web room, and to all participants for your interest, attendance, and great questions. We look forward to your participation with us again for our next monthly webinar on Thursday, July the 21st. This concludes today's webinar. Thank you.